Previously, we talked about the importance of population projections, forecasts, and estimates. I underscored their importance in long-range planning and policy making. But how are these projections made? Planners use several approaches to estimating present population and forecasting future population. Those methods and techniques most commonly include trend extrapolation, ratio share techniques, symptomatic and statistical association techniques, joint economic population techniques, holding capacity techniques, and cohort component method. In this module, we'll cover trend extrapolation, ratio share techniques, and cohort component method. These are a few of the more commonly employed methods in demography and planning practice. Trend extrapolation examines historical trends and extends them into the future, beyond the last date of the input data. The method is often used for small areas where disaggregated population statistics are not always available. This is an attractive approach for areas we call data-poor locations because trend extrapolation techniques generally have lower data requirements, low costs, and are easy to apply, making them an accessible method for smaller areas that may not have much technical capacity. Extrapolation methods can be applied not only to total population, but also to its components. That is, for components like the elderly, fertility rates, migration rates, to get a more detailed output. These methods consist of both mathematical and graphical methods. We'll focus on the mathematical method. Let's go over the growth rate method. First of all, a quick disclaimer. There will be formulas here. If you have a natural adverse reaction to seeing formulas, try to bear with me and we'll make this as straightforward as possible. Another note, my handwriting is not the greatest, and I'm going to do this as a written exercise, so hopefully you can follow along with that as well. Let's start out with the formula for growth rate. First, we start with a little r. The little r represents the annual rate of growth. That's the number of interest for us. We want to see how quickly an area is growing each year. We can then use that to kind of multiply out over time what the growth rate would be in 1 year, in 5 years, 10 years, etc., assuming all things remain equal. In economics, we call that ceteris paribus. That means if everything else stays the same, this growth rate should be fairly accurate. Next, on the right-hand side of the equal sign, we take 1 and we divide it by the variable n. N here represents the number of intermediary years, or the number of years from which we're drawing this data. And we'll talk about that in just a minute. So 1 divided by n. We then multiply that by a rate of change. And this rate of change may look familiar. If you've looked at like the percent change of new versus old, this is the same thing. When we do that rate of change formula, it's simply new minus old divided by old. Here we have the letter P, which denotes population, and we have a subscript for the letter N. N will represent the current year. So P sub N is population of an area in the current year. Subtract from that P sub O, where O is a base year, or the first year of our data, or the old number. We do that math, and then we divide that all by the population of the first year, the old number, so population sub O. And then multiply that whole thing by 100 just to get a nice clean percentage rate. So let's work out an example. Let's say the current population of any given area, P sub N, is equal to 10,000 people. The base year population, which is P sub O, is the population some number of years ago. In this case, we'll say 7,000. And let's say the difference between the number of years, or the span of time between the two observations, is from 2000 to 2010, so 10 years. If we start to fill out that formula we first saw, we just place r on the left-hand side of the equation because that's what we're solving for. Then we set this equal to 1 and divide it by the number of years, or number of intermediary years, that are of interest, in this case 10. So 1 divided by 10. Multiply that by the new population, or the most recent number, P sub N, which is 10,000. And then we subtract from that the 7,000 population, P sub O, the old population, that we first observed. That's our total change in population over this period. And then we divide that by the old number, P sub O of 7,000, to get our rate of change. And then we just multiply that by 100. So solving one more piece of this, as I said, we'll take this fairly slow. R is equal to 0.10, so 1 divided by 10 is 0.10. We multiply that by 3,000, which is the 10,000 minus 7,000 we saw before, divided by 7,000, the original population or old population, times 100. We take it one step further and we get our final numbers that we'll do the arithmetic on. R is equal to 0.10 times 0.429, and that's our rate of change over that 10-year period, and then multiplied by 100. Once we multiply those things together, R is equal to 4.29%. That's the annual rate of change we've observed for this location. Okay, now we have our annual observed rate of change. We know that population has grown by roughly 4.29% each year. Let's figure out what our population will be in another 10 years, assuming that this growth trend continues. To do that, we'll use P sub n as the notation for our future population. That'll be equal to the old population, which maybe confusingly is our new population. So the 2010 population in this case, multiplied by 1 plus that rate of change we found divided by 100 times the number of years that we're looking at. So let's fill in that formula, and if it's a little confusing, hopefully this will make it clearer. So P sub n is going to be equal to 10,000. 10,000 is our base year now in this case because we're going to extrapolate out to 2020. We're going to multiply that by 1 plus our growth rate, which is 4.29%, divided by 100 to get that in decimal form, and then multiply that by the number of intermediary years in, which in this case is equal to 10, the years between 2010 and 2020. So we do a little bit of math, and P sub n is now equal to 10,000 times 1.429. And multiply that out, and we get a final population in the year 2020 of 14,290. As we said before, extrapolation methods are pretty straightforward. They don't require a lot of technical capacity and not a lot of data either, so they're an attractive option for many locations. Another method that is useful for small areas are ratio share techniques. Here, study area population is expressed as a ratio or share of the population of a larger geographic area called a parent area. You might employ this method when you have a good future population projection for a large area, like a nation or a region, but you don't have enough data to accurately project the population of a small area. Formula for the ratio share method is a bit more complicated, but it just involves standard arithmetic, and once you know what the variables are, it's pretty easy to apply. So let's go through each one of those variables, and then we'll do another example. So we start out with a population of a smaller area in some target year. That's what we're interested in finding. We want to know what the population of some small location is in some date in the future. And we're going to base that off of its traditional relationship with growth in the larger area. If we start out on the left-hand side of the equation, we have pop sub m. That denotes population of the smaller area. We use a comma to add on to that additional information, in this case ty. That's target year, so that'll be the population in our future date. So the left hand of the formula simply denotes population in a smaller area in some target year. We're going to set this equal to population, again sub m, so of the smaller area. In this case, we're also going to denote the letters ly, and that's a launch year. So similar to our extrapolation method, we're going to start with 2 periods of time. Let's use again an example of 2000 and 2010. So we have 2 years there, and ly will denote 2010, the later year or the later base year. So this is the population of a smaller area in a later base year or launch year. We're going to add to that the growth share formula. And the growth share formula is simply population in the smaller area in the launch year minus population in the smaller area in the base year. And the base year is that first period. So in this case, this would just be population in the smaller area in 2010 minus population in the smaller area in the year 2000. So this is just the change between those two periods of time in that specific location. We divide all of that by population sub n, which is population of the larger area or the parent area in the later or launch year, which would be 2010 in this case, minus population in sub-area n, which again is that larger parent area in the base year. That's the year 2000 in our case. So what we're doing here is just dividing the change in the smaller area population by the change in the larger area population. And that's just going to give us a percentage. And what that really tells us is the percent of growth in the larger area that we can expect to attribute to the smaller area. And hopefully when we do an example, that'll be a little bit clearer if it's not clear now. So then we multiply that whole thing by the population in the larger area in a target year. That's a critical piece of information. So we're going to need to know what the population is in our target year for our larger area. So the only unknown here is what that population in the smaller area in the target year is. And so we're going to subtract from that larger area target year population the larger area launch year population, which is in this case 2010. So that's our formula. Again, a little complicated and a lot of letters that are stand-ins for numbers, but once we use it a couple of times, it should be pretty clear. Let's simplify the formula just a bit. In this case, we can reduce the share ratio down to population in the smaller area in the target year is equal to population in the smaller area in the launch year plus the growth share multiplied by population in the larger area in the target year minus population in the larger area in the launch year. And if all of that has your head spinning just a bit, let's put together a quick example to see if we can't make this a little clearer. So let's take an example of Auckland in relationship to New Zealand. And we're going to use a base year of 2000. And so the Auckland population in the year 2000 is roughly 1.2 million people. In New Zealand, that same year in 2000, the population is estimated to be roughly 3.8 million people. In 2010, the Auckland population grew to 1.6 million people, and the New Zealand population was roughly 4.3 million people. And so what we want to know here is, assuming for some reason maybe we don't know or don't have a good idea of what the Auckland population is going to be in 2020. Now, this is a little far from reality because Auckland is such a large area. We have a lot of technical capacity to measure and predict growth rates for Auckland. But if we were going to look at a smaller neighborhood or a more remote location, we might not have that data. In this case, we'll just keep it simple with Auckland and New Zealand. So let's set up our formula here. We have population of the smaller area in the target year on our left-hand side of the formula. That's what we're trying to solve for. And we're going to set that equal to population in the smaller area in the launch year. That's the last known data point for the smaller area. In this case, the 2010 population of Auckland, which is 1.6 million. We're going to add to that our growth share. And the growth share formula, again, in the numerator, or the top part of the equation, is the population in our smaller area in the launch year, so again 1.6 million, minus the population in our smaller area in the base year, which is 1.2 million. So we'll get the additional population in that decade in the numerator in Auckland. And we're going to divide that by the population change in all of New Zealand during the same period. So we start with 4.3 million, which is New Zealand's population in 2010, and we subtract New Zealand's population in the year 2000. So 4.3 million minus 3.8 million. So that's our growth share formula, and we'll work that out in a second. And then we multiply all of that by the population of the larger area, so the population of New Zealand in the target year. And we're going to say we have that information, but we'll get to that in a minute. We'll subtract from that the population of New Zealand in the launch year, so the last data point, which is 2010. And we know that population is 4.3 million. Let's go back to the target year of New Zealand population. So let's just throw in a random large number. We'll say 5.6 million people. Okay, so we just need to do a little bit of arithmetic to get the final numbers ready, to add together and multiply to get our Auckland population in 2020. So we keep on the left-hand side, again, the population of the target year of Auckland, and that's equal to 1.6 million, which is the 2010 population of Auckland. And we add to that 0.8, and that's the growth share. And what that tells us is that 80% of all the future growth in New Zealand will go to Auckland based on this historic trend between 2000 and 2010. And then we multiply that by the projected or the observed growth rate in that parent area, in this case, all of the growth in New Zealand. Now, in this case, it's a bit extreme. It's a large number, 1.3 million. That would be a very large growth rate for New Zealand, but let's just assume it's true. So we multiply 0.8 times 1.3 million. To reduce this down a little bit more, we have that 1.6 million population observed in 2010. We add to that the 80% growth of New Zealand, which is 1,040,000 people. Add those together and we get a total population in the target year for Auckland of 2,640,000 people. And that's how we figure out the share of growth a smaller location will get of the larger area's population and project a final or target year population. Notice that both trend extrapolation and ratio share methods allow you to develop projections for the future population. In either of these, there's not a consideration or space for adding potential effects of policy or other exogenous effects that may alter that trend line. A method that is commonly used for demography that has the ability to capture some of these effects is cohort components method. This method gets its name from the way it disaggregates population change into component parts. First, the population is divided into separate age groups, genders, and ethnic groups called cohorts. Then, population is divided into its components, which includes deaths, births, and migration. It should be a bit clearer at this point how policy effects might be introduced to this method to develop a forecast. We can use the cohort component method to capture the population effects of a change, for example, in migration policy, or capture the effects of a strong economy in one region that would reduce the migration to another region. A basic component model may look something like this. If we add to this basic formulation information about the size of population in each age group and the age-specific probabilities of giving birth, dying, or moving, the resulting methodology is known as the cohort component method. The cohort component model is considered to be a fairly sophisticated method. As such, it is also a data-intensive model. So what kind of data goes into something like this? Some data sources, especially on births and deaths, are often well measured by vital statistics registration systems. Administrative data captures most of the legal immigration into a country. Inside the country, though, there's seldom a direct measure of internal migration. So it must be estimated using an indicator variable based on alternative data devised for another purpose. That data needs to provide addresses for individuals at two different points in time. Some sources of such data may include things like changes in postal address, driver's license records, tax returns, or health insurance information. So which method should you choose when you're developing projections or forecasts, and what's the data source? This depends on the data available. So some things that you might want to consider is, do you have data that is a primary source of data or a secondary source of data? Primary sources of data are things that are originally collected often by a planning agency and are generated through its own form of data collection. So this might be enumeration or sampling. Secondary data, that's things like the census, are estimations based on indirect indicators. It's commonly said that even the best data and methods available to planners are completely worthless if you can't show that data to an audience and have them understand it quickly. So, once you have gathered population data, or you've created detailed projections or forecasts, how do you visualize it for yourself, for your colleagues, or for a more general audience? One approach is called a population pyramid. A population pyramid is a paired bar chart type graphic that shows the numbers or percentages of males and females in each age cohort. This type of graphic provides a very clear picture of a population's age-sex composition, which is one of the key measures for demography. The use of a population pyramid is considered to be the best way to graphically illustrate the age and sex distribution of a given population. There are generally 3 types of population pyramids created from age-sex distributions, and they can tell you a lot about your population. First, there's the expansive population pyramid. This population pyramid shows larger numbers or percentages of the population in younger age groups, usually with each age group smaller in size or proportion than the one before it. These types of pyramids are usually found in populations with very large fertility rates and lower average life expectancies. In extreme cases, like we saw in Japan, you might see in the future an inverted expansive pyramid, showing the top-heavy aged population and a relatively smaller younger age cohorts below. Second is constrictive population pyramids. These pyramids display lower percentages of younger people. Finally, a stationary pyramid or a near stationary pyramid displays somewhat equal percentages for almost all age groups. Of course, smaller figures are still to be expected in the oldest age groups. While these are just a few of the ways in which the science of demography interacts, enables, and enhances the field of planning, there are many more ways in which the two fields are important to each other. As we move on in the semester, we will continue to explore the way that we think about, model, and plan for future change.